Hello everyone, this video is the 8th in my series explaining AIME problems. In this video, I'll be talking about number theory problems that are more algebra-based and the ways that they can be solved. I encourage you to pause throughout the video and try to solve the problems. Here are some general tips for algebra in number theory. Always look for the words a positive integer, usually that symbolizes a need for number theory. Also, try to look for simple Diophantine equations, which I explain later, in algebra problems. These can be solved quickly with number theory. Also, try to look for ways to generalize an algebra problem. Sometimes a number theory problem may come when none is expected. And problems with fractions that seem too complicated can sometimes be solved pretty quickly with number theory. Now I'll explain what Diophantine equations are, in preparation for the next problem. A Diophantine equation is a polynomial equation with integral coefficients and positive integral solutions. And to solve linear Diophantine equations, you have to take the modulus of the coefficient that comes up the most, because that'll be the easiest to find, and then find the solutions from there. And you can also repeat it if needed. And there are similar solutions for nonlinear equations. Examples of some Diophantine equations are 5m plus 3n equals 23, 20n squared plus 7m squared equals 27, and x to the fourth plus y cubed equals 1. Now let's solve a problem that involves a linear Diophantine equation. Find the number of ordered pairs of positive integer solutions mn to the equation 20m plus 12n equals 2012. First, there's a common factor of 4, so we can divide that out. We get that this equation equals 5m plus 3n equals 503. Now, let's take a mod 5 of this equation. This becomes 5m plus 3n, which is congruent to 3n, which is congruent to 503, which is congruent to 3 mod 5. So, n is congruent to 1 mod 5, which you can see by doing 3n minus 3 is congruent to 0 mod 5, or 3 times n minus 1 is a factor of 5. So n minus 1 has to be a factor of 5. Now, that means then that n can equal 1, 6, 11, all the way up to 503 minus 5 over 3, which is 166. And the number of terms in this sequence is the answer. And we get that the number of terms is 166 minus 1 over 5 plus 1, which is 34. Now let's solve a problem where the number theory is kind of hidden. Find the number of rational numbers r, 0 is less than r is less than 1, such that when r is written as a fraction in lowest terms, the numerator and the denominator have a sum of 1000. So let's quantify these restraints. For a fraction, a over b, we have that a plus b equals 1000, a is less than b, and the GCD of a and b is equal to 1. So we can rewrite this as the GCD of a and 1000 minus a is equal to 1. And we can use the Euclidean algorithm, which states that the GCD of x and y, where x is less than y, is always equal to the GCD of x and y minus x. So we can do this in a reverse format. We can add a to this expression. So this becomes that the GCD of a and 1000 has to equal 1. So a is relatively prime to 1000. And a is less than 1000 minus a, or a is less than 500. Now, there's a formula to figure out how many numbers are relatively prime to a number. And that is, You take the number and you find its primes, which are in this case 2 and 5, and you put it in this formula. 1 minus 1 half and 1 times 1 minus 1 fifth. So you subtract 1 over the prime from 1 and multiply each of those terms together and multiply that by the first number. And this equals 400. However, we have to divide by 2 because exactly half of them are under 500. So our final answer is 200. Let's do another problem in which the number theory is also hidden, but there's not as much number theory in this problem. The repeating decimals 0.ABAB and 0.ABCABC satisfy this formula, where A, B, and C are not necessarily distinct digits. Find the 3-digit number ABC. Before we start, we have to find some way of simplifying these two terms. And there's a really clever way of doing that. If we set x is equal to 0.ABAB, then let's do 100x, which equals AB dot AB. Repeating. And if you subtract the first term from the second, then we get 99x equals AB, or x equals AB over 99. And similarly for the other term, this equation turns into AB over 99 plus ABC over 999 equals 33 over 37, which equals 891 over 999. Now we can multiply this whole expression by 999. And doing that, we get, and simplifying, this equals 111 AB over 11, not 111, 11, plus ABC equals 891. And now we see that A has to equal B since they're digits and divisible by 11. And just trying out some digits, we see that the only number that's possible is A equals B equals 4. And this comes out to 444 plus 44C equals 891. And we get that C equals 7. So our final answer, which is ABC, equals 447. Let's now do a problem that involves generalization. Find the smallest positive integer n with the property that the polynomial x to the fourth minus nx plus 63 can be written as a product of two non-constant polynomials with integer coefficients. This polynomial, since it's a quartic polynomial, we can write it as a product of two quadratic polynomials or the product of a linear and a cubic polynomial. So let's start with the first one. For the quadratic, let's generalize it as x squared plus ax plus b times x squared plus cx plus d. And after simplifying, we get x to the fourth plus a plus c x cubed plus b plus d plus ac x squared plus ad plus bc x plus bd. And after we equate coefficients, we get that a plus c equals 0, b plus d plus ac equals 0, ad plus bc equals negative n, and bd equals 63. Solving with this and plugging in here, we get that b plus d equals a squared and bd equals 63. And considering b is less than d, let's find the possible values. B can equal 7 and 1, and D can equal 9 and 63. And these are the pairs. And for these pairs, A equals 4 and A equals 8. And plugging this into the value for n, we get that the possible values for n are n equals 8 and another value of n that's much larger. So right now our lowest value is n equal to 8. Now let's explore the other case. The other case is the product of a linear and a cubic factor. So that would be x plus a after generalization times x cubed plus ax squared or plus bx squared plus cx plus d. Simplifying, x to the fourth plus a plus b x cubed plus ab plus c x squared plus ac plus d x plus ad. Equating coefficients, we get that a plus b equals 0, ab plus c equals 0, ac plus d equals negative n, and ad equals 63. Solving this, we get c equals a squared, and plugging into this, we get a cubed plus d equals negative n. Also, d is equal to 63 by a, so we get that a cubed plus 63 by a equals negative n. And the smallest value that's possible for n is 48. But this is much larger than 8. So our final answer is just 8. Now let's do a problem that seems difficult but can be solved pretty easily. For a positive integer n, define the positive integer to be p-safe if n differs in absolute value by more than 2 from all multiples of p. For example, the set of 10 safe numbers is 3, 4, 5, 6, 7, 13, 14, 15, 16, 17, 23, and continued. Find the number of positive integers less than or equal to 10,000 which are simultaneously 7 safe, 11 safe, and 13 safe. Now, how can we represent this restriction on the numbers? Well, since this is a number theory problem, let's try to use mod. It has to be p-safe if it does differ by more than 2. So that translates to any n is greater than or equal to, or congruent to, 3, and it's less than or congruent to p minus 3. And this is mod p. So for 7, 11, and 13, n has to be congruent to 3 or 4 mod 7, and has to be congruent to 3, 4, 5, 6, 7, and 8 mod 11, and n has to be congruent to 3, 4, 5, 6, 7, 8, 9, and 10 mod 13. Now, how can we use this information? Well, first let's try to find how many total modular residues there are. And by the Chinese remainder theorem, there's going to be exactly 7 times 11 times 13 unique numbers that have these modular residues. And this equals 1001. So for each 1001 numbers, there are 2 times 6 times 8 possible values, which equals 96. So there's going to be 960 since 1001 times 10 equals 10,010 values. But we have to subtract any values that are there between 10,000 and 10,010. And we find two values, specifically 10,006 and 10,007. So our final answer is 958. Thank you for listening. Please like and subscribe, and remember to click the bell icon for more updates.